A vector is drawn as a straight arrow on a coordinate system. They are named with bold lowercase letters, typically U, V, W. V is the standard for vector. U and W are also used because they're right next to V. A arrow above a pair of letters, where the letters really stand for the starting and ending points, also designates a vector. So something like BD, B would be the starting point, D would be the ending point, and the line shows that it's a vector. It's an arrow. Now, vector arrows have a certain length, and these are called magnitude. And they also point in a certain direction. These do not need to start at the origin, unlike polar coordinates. So polar coordinates, you can kind of think of them as a vector, right? It has some angle and then some length out, and that's the point. The vectors don't have to start at the origin. They can be anywhere on the plane. It's just as long as you draw an arrow. So let's consider this vector here labeled U, or you could also say AB, the same thing on this graph. You can see that this is not starting at the origin. So this cannot be really described with polar coordinates as it is now, but it is still a vector. It has a certain length. This length here is the length of the arrow, and it points in this direction. That's what the arrowhead is for. Now, two vectors are actually equal. Two vectors are equal as long as they have the same magnitude and the same direction. Doesn't matter where they are on the plane, as long as they're the same length and the same direction that they point, you get the same vector. So what I can do is I can take this point here, shift it over and down. So it's going to start here, and take this point and do the exact same movement. So that we went over this way and then down. We're going to go over this way and then down. So we're going to shift it to this point here. And that gives me the vector, something like this. I can draw straight. That gives me the vector. And this has the same magnitude, the same direction. I can label this with U as well. It's the same thing. It's the same vector. And specifically, this vector that I have drawn here, it starts at the origin. This is what gives us the position vector, because it kind of tells us the position of the end point. The starting point's always going to be 0, 0. The end point is where it's pointing to. Now, we can use polar techniques on this vector because it's on the origin, and we can get really the quantities that define this vector. The direction, in this case, we're going to use the angle, and the magnitude, which is going to be the radius here. Okay, you can see that this end point here is at -2, 3. So the radius is going to be the square root of -2 squared plus 3 squared. So it's going to be 4 plus 9, which is the square root of 13. Of course, you can plug it in a calculator, get an answer for that. Now the angle, the direction, is going to be the inverse tangent of y over x. Y is 3, x is -2. Of course, we're going to have to be careful with this because it's going to be in the second quadrant, and when we do the inverse tangent of this, I'm going to do it in degrees here. I get -56.31 degrees. Of course, this is not correct. This is going to be in the fourth quadrant. But to do that, all we have to do is do 180 minus 56.31. That's going to give us, we get 123.69 degrees. And that's the direction. We have our magnitude. That is everything we really need to know about the vector U. Now, if a vector is a position vector, then we can write it as an ordered pair. We don't actually have to write it in any kind of special way. We don't have to just show it, because for instance, this one here, right? We know it starts at the origin. So the ending point is going to be the location of this coordinate. So really the only thing that we need to know about this vector is the ending coordinate, and that's why you can write it as an ordered pair. So you can write it, of course, just with coordinates, but typically with vectors, to just designate they're a different type of thing. They're not just points; they're actually arrows. We use these kind of brackets, these angle brackets. Okay, we can see that we have polar coordinates for this vector, and we have rectangular coordinates for this vector. But both of these require position vectors. They have to have these position vectors for them to be used this way. But any general vector doesn't have to be on the origin, so most vectors don't satisfy this requirement. So what do we do in this case? Well, to better describe this, what we're going to do is we need to have unit vectors. These are vectors that have a specific direction. It's actually, the direction is very important for a unit vector because it's going to define everything else, every other kind of vector. But we're going to have a magnitude equal to 1. So really the main idea of unit vectors is the direction. A magnitude equal to 1 means that it's not going to change much, if you will. Think about like multiplying by 1. It doesn't do anything, but the direction does. Now, Cartesian coordinate system is a two-dimensional system, so we have to have two unit vectors to define any general vector that we want. And the way we do this is we actually have the standard unit vectors you can use. You can use any really two vectors as long as they're not parallel vectors. You can use any two vectors, but the standard ones are going to be I and j. I is going to go in the positive x direction. It's going to point to 1. That's a length of 1, right? So that means that this is going to be the vector 1, 0. Or use coordinate, the coordinates. And then j is going to be the vector 0, 1. So it's going to point in the positive y direction. So unit vectors are going to be always position vectors. We want them to be position vectors because we always want them to kind of show us where the starting point is. And every coordinate system has a starting point called the origin. So the origin is very important for working with unit vectors. Now we can think of these as these vectors, I and j, as the building blocks for every other type of vector. When we have any kind of general one, you can break it down into just transformations, either being it's stretched or compressed, or as we're going to see, we're going to have to do operations on these things of these unit vectors. So that's the way I want you to think about it, and we're going to look at that some more here. Now, we need to define vectors using these unit vectors, and to do so, we're going to have to understand what is vector addition. And this is best described visually. So here I have v, and v really is just I and j. So we're going to say I plus j. That's what v is. And the way you do that is you either can take because it's I plus j, it's kind of natural to think of I first. We're going to take I, and then any vector is the same vector as long as it has the same direction and magnitude. So all I've done here is I've shifted j to be this j here. Now this j, I wouldn't call this a unit vector. It's a unit vector in the same sense that it points the same direction and it has the same magnitude, but it's not a position vector. That's fine though, because we're doing unit vector addition here, so we can't have position vectors for this. We have to, for either I or j, move it off of the standard position. So the way we can do this is we can either just add on I, and then we go up to j, and the resulting vector I plus j is going to be from the initial starting point and pointing at the end point. That's why we have this. That's what I've shown here. Now, of course, you can go j plus I, since addition is commutative, and we get the exact same vector. So that's the basic idea of vector addition. You're just putting one vector on the end of the other vector and then creating a line. So v is 1, 1. Because it's, and this is the position vector of v as well, because it starts at 0, 0 and goes to 1, 1. Now, if we had I plus I, instead of having I plus I, really, this is just the same thing as 2I, because it's just going all the way to 2 now. J plus J is really just 2J. It's just going up 2J from that position. And with this, 2I and 2J, well, you can see that really I plus I is 2I. And the 2 there, really what that's doing is that it's extending the vector by a factor of 2. So no longer does it have a magnitude of 1. Now it has a magnitude of 2. And that's the idea of this number multiplying a vector. And this number is called a scalar. And in terms of vectors, it's really just a directionless magnitude. So it's just a number. And this is an important distinction between numbers that you normally use in any kind of sense. They're really called scalars. And vectors are numbers with a direction, magnitude with a direction. That's the idea. And that's kind of the simplest idea of scalars and vectors. Also, what vectors are is with just direction. They can be a lot more than that. They're very powerful. But for a first introduction, this is the best way of kind of thinking about it. So when you multiply vectors by scalars, we're really just stretching or compressing the vector in the direction that it is pointing. So here we stretched I by a factor of 2. It just increased it to a length of 2, but it didn't change the direction. The same thing happened for 2J, right? The same direction was there, but it just stretched it by a factor of 2. And any scalar multiplying will work. So we have, any kind of number you want to multiply by. It doesn't really matter. Negative numbers we need to talk about more, though, because we haven't looked at any kind of negative effect. So to do so, let's consider the case where we have I plus W, some vector W equals 0. I is the standard unit vector. Now 0 this is a bold 0. This is going to be the 0 vector. Think of it like a magnitudeless direction. It's really just the origin, and you have to have a vector being a 0 vector in order to work with vectors, because you need to have a 0 in the system, and that's what this is doing. But to have I plus W, right? If W must be the exact same magnitude but the opposite direction of I, so that when you add I plus W, right, we go out to I and we go back from I to W, and it's going back to the origin. So that gives us the 0 vector back. But with this in mind, really W is just the opposite direction of I. It's the same length, but opposite direction. And so we don't actually need a different symbol for this. Really, all we need to do is say that W is negative I. And that's what a negative will do to vectors. All it does is it flips the direction of the vector. It leaves the magnitude the same, unless, of course, you're multiplying by like negative 2I. But just a negative will flip the direction of the vector. Now, with this, we can finally describe U, that very first vector that we looked at, it was negative 2, 3, with the unit vectors. So what I have here is two different ideas. It's really the same thing of getting U from the unit vectors. Really, there's two components of negative I, because we're going backwards. We're not going in the forward direction, the positive x direction. We're going in the negative x direction. And then there's 3 components of j. That, of course, just looks like this. But we have like terms here, and that gives us negative 2i plus 3j. Negative 2i just flips the direction of I and extends it by a factor of 2. And 3j just extends j by a factor of 3. So if we add these two up, you can also add 3j first and then negative 2i, and that will give you u. Either way you want to do it, it gives you the exact same answer. And what's nice is that this expression here does not need a position vector. It is perfectly definable no matter where u is at. So if I were to draw u somewhere off, like here's the coordinate system, and I were to draw u down here, it would still be 2i or negative 2i and 3j. It doesn't matter if it's on the origin or not. And that's the beautiful thing about this form, is that I will always describe the vector without any ambiguity.